All right, hopefully you're still with me. We've set out some definitions, some vocabulary, and I'm trying to connect them to sound to make those quantities stick a little bit better. Amplitude is related to the energy and it's related to volume. Frequency is related to pitch. It's how high or low. And then the two new ones, the speed of the wave and the wavelength. We're going to kind of circle back to those. We literally are going to do a math proof. We're going to come up with a cool equation. I don't know how to embed videos inside videos, so you can pause this video and watch that video of me doing the proof. And I've also typed it out here. Well, I typed it out, then I thought it was kind of dumb to type a proof, so I made the video afterward. Watch one of those, but basically I'm going to go through real quick in this one. Speed is always distance over time. We know that the distance of a wave is this new thing called wavelength. And we know that the time of a wave is kind of related to frequency. Frequency is number over time, so we could say that one wave, since it's got time on the, if we're talking about one wave, frequency is 1 over time. So when V equals d over t, wherever we see d, put in lambda, and for the 1 over t, we can replace the whole 1 over t with frequency. Watch the other video, read through the typing a little bit slower, but we get this cool new equation called the universal wave equation. It works for any kind of wave. V is equal to F lambda. If we know the speed that wave propagates at, then there's a connection between frequency and lambda. As one goes up, the other goes down. If we know two of these three quantities, you can calculate the third. There's an example there. You can watch that video. There's 3 questions to try. But here's the key concept that I want to talk about in this video today. The speed of a wave depends on a medium, and unless we start messing with the medium, that usually means that the speed of the wave is constant. So let's say you're in your house right now, you're playing with a ruler, wobbling it on the edge of your desk. You're not changing the air in your room, so you're not changing the medium. So the speed of the sound waves that the ruler makes when it's wobbling, the speed of those sound waves is going to be constant. Really what the wave equation does is it gives a connection between frequency and wavelength. Here I'm going to doodle it in math over here. V is equal to F lambda. If you do something to make the frequency get higher, so let's say frequency increases, since frequency and wavelength have to multiply to make the constant speed, to make the same speed number, if frequency increases, then the lambda is going to decrease. So if you do something to make a high frequency sound, generally speaking, a high frequency sound is going to have a shorter wavelength. And then the flip-flop, if you do something to make the frequency, so maybe hang more ruler off the edge of your desk so it's vibrating at a lower speed, if you decrease the frequency, sorry, at a lower frequency, I got to be careful when I use the word speed. If you decrease the frequency, then as a result, the wavelength will be longer. Basically, what we're going to see moving forward is that because we can often consider the speed of a wave to be constant, there's a connection between frequency and wavelength. High frequencies have short wavelengths and vice versa. Low frequencies have long wavelengths and vice versa. So the connection to music, and I think we're pretty much done the theory for today. Make sure you practice using that wave equation. But the connection to musical instruments, let's say you have a really, really long instrument. So musical people picture a long instrument. So like your tuba, the trombone, long instruments. Long instruments can fit a longer wavelength in them. And because those are longer wavelengths, long instruments play a lower frequency. On the same notion, your shorter instruments, so your flutes, piccolo, if you're a saxophone player, like your alto sax compared to your tenor sax, those instruments that are literally shorter in length, in the shorter length of those instruments, we end up with shorter wavelengths. Shorter wavelengths means higher frequencies. They play the high notes. So the big long instruments have longer wavelengths. They play the low notes. The shorter instruments end up with shorter wavelengths. They play the higher notes. I don't think it's next lesson, but we're going to come back to that connection to the length of an instrument and the wavelength. We're going to come back to that and actually do math on that soon. I'm going to keep cruising and finish it off here, but what hasn't come up yet is that there literally are different kinds of waves. In grade 11, we're going to focus on the two main kinds. There's something called transverse waves. Those have been the waves that I've drawn over and over again. Mine's not animated, but open your Google document, and this is a cool animation. Things are wobbling up and down. It's a little bit hypnotic. If you look closely at it, there's little red dots in this animation at different points. And now that I've highlighted it, I'm not seeing them. Oh, here's one over here. Kind of zero your eyeball on those little red dots, and you'll see that they're literally just moving straight up and straight down as the energy moves sideways. So the particles are vibrating up and down. That's the direction of the vibration. So I'm going to put F for the frequency of the vibration, but the energy is moving sideways. So V for the energy speed. They're perpendicular to each other. That's a transverse wave. That's a classic water wave. The particles are vibrating one direction, up and down, and the energy is moving horizontally or perpendicular to that. The other kind of wave that I haven't drawn yet, but we're going to start drawing because it's what a sound wave is. Sound waves are what we call longitudinal. Oops. The vibration is parallel to the direction that the energy is moving. So again, mine's not animated, but at home yours is animated. This red plate back here, or open the Google Doc, this red plate back here is going to vibrate, but it vibrates back and forth. So this would be like if you could take, if you had a speaker, like an old school big speaker, if you could see the cone of the speaker wobbles back and forth. Or imagine a tuning fork, the tuning fork wobbles back and forth. Or maybe this is the string of your guitar wobbling kind of back and forth. As that thing wobbles back and forth, that makes the air particles in front of it wobble back and forth. That creates places where there's a whole lot of air particles kind of bundled, squished together, and then places where there's not so many air particles and they're kind of spread out. So a bunch of air particles squished into here, less air particles through here, and a bunch squished into here, less into the next spot. We're going to call that a transverse wave, we're going to call that one a longitudinal wave. The vibration of the thing that's driving the sound wave is parallel to which way the particles are vibrating. This is exactly what a sound wave is. Now there's a bunch of typing in here, but basically as this, whatever's driving it, wobbles back and forth, it changes the distribution of the air particles. It makes chunks of air that are slightly higher pressure and chunks of air that are slightly lower pressure. Back to my diagram, this kind of chunk right here would be a high pressure, another high pressure here, another high pressure here, and then in between it would be the low pressure here, low pressure there, low pressure there. If I had some sort of special pressure meter, and I put my special pressure meter kind of right here, eventually my special pressure meter will be hit with a high pressure. And then a split second later, it'll be hit by a low pressure. And a split second later, it'll be hit by a high pressure and a low pressure. So it would alternate high, low, over and over and over again. If my special pressure detecting machine was actually your ear, that alternating high pressure, low pressure is literally going to push your eardrum back and forth. And as your eardrum wiggles back and forth, that's connected eventually, 3 small bones, lots of cool biology, that's connected to some nerves that take it to your brain. And based on how quickly that eardrum is vibrating, pushed back and forth from those high pressures and low pressure, your brain decodes the sound. Is it a high pitch or a low pitch? If it's a really, really high pressure, that's a high amplitude, that's going to be loud. If it's not such a high amplitude, it's still a high pressure pushing your eardrum in, a low pressure pulling your eardrum out. But if it's not so high amplitude, it's not pushing it as far, your brain decodes that as not as loud. So that's the second kind of wave. They're uglier to draw, but that's really what a sound wave is, a longitudinal wave. That's where I'm going to pause the video. There's this check-in you're going to do on this whole big topic. There's a lot in this one, so take your time going through it. Reach out to a friend if you think it'll help. And as always, if anything's bugging you, shoot me an email and we'll sort it out together.